During the Second World War, the escalating Allied bombing campaign forced Germany and other Axis powers to rethink their air strategies, shifting many fighters from air superiority roles to bomber interception. This transformation demanded weapons, far more destructive than the smaller caliber machine guns used early in the war. The German answer was the Mk 108-30 mm autocannon, a weapon that dramatically increased the odds of destroying a heavy bomber with just a few rounds. Compared to the 20 mm Mg 151, which required dozens of hits to down a bomber, the Mk 108 could achieve the same effect with as few as 3 to 5 strikes. Its high explosive and incendiary ammunition inflicted catastrophic damage by tearing apart wings, rupturing fuselages, and igniting fuel tanks at temperatures exceeding 1,200 degrees Celsius. British testing confirmed that both fighters and medium bombers hit with 30 mm rounds suffered lethal structural failures, while U.S. data and post-war surveys highlighted the weapon's effectiveness against American B-17 and B-24 formations. In Europe, however, the advantages of sheer firepower came at steep costs. The Mk 108's low muzzle velocity meant rounds dropped heavily over distance, forcing German pilots to close into short ranges, where they became vulnerable to defensive .50 caliber machine guns and long-range escort fighters. Its slower rate of fire, limited ammunition capacity, and the burden it placed on aircraft performance further reduced overall effectiveness. In the end, the Mk 108 embodied both the strengths and weaknesses of late-war German air strategy. It delivered devastating, often fatal blows to Allied bombers, but it also exposed Luftwaffe pilots to high risks, contributing to mounting losses as the tide of the air war turned against Germany. This video explores in depth how the German Mk 108-30 mm autocannon influenced the effectiveness of Luftwaffe fighters against Allied heavy bombers during the Second World War. In the early years of the conflict, Axis fighters were designed mainly for engaging other fighters. But as the air war intensified and Allied strategic bombing campaigns escalated, the need arose to transform these fighters into bomber interceptors. This change demanded far more destructive firepower than the small-caliber machine guns that had originally armed many Axis aircraft. To knock out large and heavily armored bombers such as the American B-17 Flying Fortress and the B-24 Liberator, a shift toward larger autocannons was inevitable. A clear example of this trend can be seen in the Japanese Nakajima Ki-84, codenamed Frank by the Allies. According to a 1947 unclassified report, the Ki-84 underwent a clear pattern of armament upgrades that mirrored the overall arms race of the time. At first, the Frank was delivered with two 12.7 mm machine guns along with two 20 mm autocannons, but this configuration soon proved insufficient against the durable Allied bombers. To improve effectiveness, the aircraft was later fitted with 420 mm autocannons, and in its most advanced versions, it carried two 20 mm and two 30 mm autocannons, demonstrating the steady demand for heavier striking power. German aircraft followed a very similar path in terms of firepower evolution. Initially equipped with 7.92 mm and 13 mm machine guns, German interceptors found that these smaller rounds lacked the stopping power needed to cripple Allied heavy bombers. Machine gun fire often inflicted damage but rarely achieved the immediate destruction required to stop the bombers from releasing their payloads. As a result, the Luftwaffe transitioned toward mounting autocannons, whose explosive shells inflicted far more devastating damage upon impact. This led first to the widespread adoption of the Mg 151/20, a 20 mm cannon, and then to the even more destructive Mk 108-30 mm autocannon. The physical difference between the 20 mm and 30 mm rounds was substantial, and images comparing them reveal the leap in destructive capability that came with the larger caliber. The larger shells were designed to shatter airframes and ignite fuel tanks with just a few hits, dramatically increasing the chances of downing a bomber with fewer rounds fired. Evidence of this increased firepower can be found in a declassified 1945 tactical deployment report prepared by the 8th Army Air Force. This document recorded data from American bombing missions flown from bases in Great Britain, where both B-17 and B-24 bombers operated in mass formations. The chart included in the report provides two important measures of German interceptor performance. First, the plotted line indicates the percentage of enemy fighters that managed to score hits on the bombers with either machine gun bullets or cannon shells. This measure reflects how effectively the German aircraft were able to penetrate defensive formations and line up their attacks. Second, the vertical columns in the chart represent the number of bombers destroyed for every 10 encounters, which highlights the lethality of those engagements once combat had been initiated. Over the course of the conflict, the ability of German fighters to break through and land hits on Allied bomber formations steadily declined. This drop can be attributed to several critical factors. The introduction of long-range Allied escort, fighters such as the P-51 Mustang, which provided protective cover deep into German territory, the declining skill level of Luftwaffe pilots as experienced veterans were lost and replaced with less trained recruits, and the overall attrition of German aircraft and resources as the war dragged on. These factors combined to reduce the frequency and accuracy of German attacks on bomber streams. Yet, even as their opportunities to attack decreased, the potency of German strikes grew significantly when they did occur. This was the result of heavier armament, especially the use of the Mk 108 30mm cannon, and increasingly refined attack tactics that aimed at maximizing the limited chances available. The overall picture that emerges is a paradox. German interceptors became less successful at engaging bombers on a broad scale, but when they did manage to fire effectively, their attacks were far more lethal than before. It is important to note that the data used in the report was derived from bombers that returned to base, meaning there is an inherent survival bias, as destroyed aircraft were not part of the recorded statistics. Additional insights come from combat footage and operational records, which suggest that it typically required around 20 to 25 hits from the MG 151 20mm cannon to bring down a heavy bomber. In stark contrast, the Mk 108 30mm cannon could achieve the same result with only 3 to 5 hits. This difference illustrates the enormous destructive leap provided by the 30mm round, whose high explosive filling was designed to tear through critical structures and detonate inside fuel, tanks or near engines. German fighters could also vary their firepower depending on mission requirements by loading ammunition belts with different combinations of armor-piercing, high-explosive, and incendiary shells. A German Luftwaffe document from June 1944 illustrates 3 main categories of autocannon ammunition tailored for use against aircraft. The diagrams showed, for example, an armor-piercing shell impacting the thin skin of an airframe, providing a visual explanation of how different ammunition types were intended to maximize effectiveness against varying targets. This layered strategy of firepower development underscores the degree to which the Luftwaffe, like its Axis counterparts, sought to counter Allied bombing campaigns by evolving its fighters into highly destructive bomber interceptors. When a projectile of this type strikes the skin of an aircraft and manages to push through into a fuel tank, the result may only be a fuel leak without immediate ignition depending on the conditions inside the tank. One illustration portrays a high-explosive mine round exploding against thin aluminum skin, demonstrating how such a detonation compromises the structural integrity of the aircraft. The 30mm mine round operates on the same principle as the 20mm version, but is much larger and more destructive. Although a 30mm example is not shown here, the smaller MG 150 120mm mine round serves as a useful example of how the mechanism works. This cartridge is presented both as a complete round and as a cutaway model to reveal its internal components, including the casing, primer, propellant, and the drawn steel shell of the projectile, which houses the explosive charge and a threaded fuse. When fired, The projectile is propelled through the cannon barrel with expanding gases, forcing it outward, while the hollow design of the shell allows it to carry around 18 grams of explosive. The fuse is engineered to set off the charge roughly 1/10,000th of a second after contact with the bomber's outer skin, a delay just long enough for the round to burrow partway into the surface before detonation. Once triggered, the projectile bursts apart into dozens of steel fragments that scatter in all directions. These fragments, combined with the explosive blast, compromise the aircraft by weakening the airframe, disrupting its aerodynamics, damaging control systems, puncturing vital components, and threatening the lives of crew members within. Photographs from combat damage assessments show that a single 20 mm mine round could punch a hole in a Spitfire's fuselage nearly the size of a pilot's face, with powder burns radiating from the center of the blast, and splinter exit marks clearly visible on the inner side of the fuselage. This underlines just how damaging even one 20 mm round could be. The channel has an additional video dedicated to explaining in greater detail the destructive power of German 20 mm autocannons on American heavy bombers, but it is worth emphasizing here how much more destructive the 30 mm rounds were compared to the 20 mm. The larger 30 mm projectile carried 85 grams of explosive filler, which is nearly 5 times the charge of the 20 mm round. The explosive payload alone was about 1.5 times greater than the contents of a typical pineapple-style fragmentation grenade of World War II. Although the fuse of the 30 mm mine functioned in the same way as the 20 mm fuse, the larger size of the projectile and its greater explosive volume meant that the destructive potential was magnified considerably. Diagrams comparing the two cartridges show the massive increase in size from the 20 mm to the 30 mm, reinforcing the leap in power that German interceptors gained by equipping the Mk-108 cannons. Another visual explains the effect of a 30 mm incendiary round. In this case, the shell pierces the skin of the aircraft, enters a fuel tank, and explodes, releasing its incendiary contents. The filling of the incendiary was made from a thermite-like substance designed to burn at approximately 1,200 degrees Celsius, hot enough to ignite fuel or oil instantly. The fuses used on such incendiary shells were hydrostatic, a clever design intended to trigger the detonation once the round encountered the liquid resistance of a fuel, oil, or hydraulic tank. German ordnance manuals and charts reveal that interceptor squadrons carefully selected ammunition belts according to expected targets. For bomber interception, the Mk-108's ammunition was typically loaded in a 50-50 combination of high explosive mine rounds and incendiary rounds, ensuring both structural damage and the high likelihood of igniting fuel fires. Armor-piercing variants of the 30 mm were generally not favored for air combat since the primary targets were large bombers with expansive fuel tanks and aluminum skin rather than heavily armored vehicles. Although the Mk-108 was devastating, in terms of destructive power, it was not without significant disadvantages. The cannon suffered from a relatively low muzzle velocity of about 540 meters per second, or around 1,770 feet per second, which made it less accurate at long range and required pilots to close in more closely before firing. The rate of fire was slower compared to some other weapons of the era, and the ammunition capacity was limited, meaning pilots had fewer opportunities to strike effectively before running out of rounds. Despite these shortcomings, when the Mk-108's projectiles connected, their ability to destroy or cripple a heavy bomber with only a few hits made them one of the most feared weapons in the Luftwaffe arsenal. The Mk-108 cannon was capable of firing at a rate of about 650 rounds per minute, but because of the relatively low velocity of its projectiles, German bomber interceptors had to get much closer to their targets before opening fire. This shortcoming forced pilots into dangerous ranges where they were within reach of bomber defensive gunners and Allied escort fighters. An example of this configuration is seen in the Messerschmitt Bf 109K6, which mounted 3 Mk-108 cannons. 2 of these were installed in the wings, while a third was mounted centrally to fire through the propeller hub. This center-mounted weapon actually extended into the cockpit itself, running between the pilot's rudder pedals, a reminder of just how much space these heavy cannons demanded. German tests harmonized the wing-mounted Mk-108S so that their trajectories converged at a distance of around 400 meters. At that range, the heavy 30 mm round dropped approximately 11 feet before reaching its target. To put this into perspective, the American B-17's .50 caliber machine guns were effective at around 600 yards, and at 400 meters, a .50 caliber round dropped just over 4 feet, far less than the MiG-108's shell. The reason was the .50 caliber's much higher muzzle velocity, nearly 60% faster than that of the 30 mm round, which gave it flatter trajectories and longer effective range. The British, recognizing the threat of these weapons, conducted their own evaluations to better understand how devastating Mk-108 rounds could be. In one demonstration, a Spitfire wing was fired upon with a German 30 mm high-explosive tracer round. The projectile burrowed into the wing structure before detonating, severing the critical span-wise load paths in both the upper and lower skin. The resulting explosion compromised the strength of the wing and degraded its aerodynamic capability, meaning that such a hit would almost certainly be fatal to the aircraft. Other tests revealed the terrifying overpressure effect of a 30 mm mine round exploding inside an enclosed fuselage section. The confined gases created by the blast ripped apart the structure from within, forcing skin seams to unzip and breaking apart the internal frames and stringers. Photographs from these trials clearly show the exit damage caused by fragments bursting outward from the explosion site. Further testing against a Bristol medium bomber revealed that fuselage damage from a 30 mm hit was catastrophic. The primary load-bearing elements of the airframe, both longitudinal and circumferential, were severed, leaving the structure unable to carry operational loads. The wing of the Bristol bomber was also targeted with an incendiary version of the Mk-108 round. Even though the fuel tanks were drained during the test, the structural damage was assessed as lethal. When trials were carried out against a fully fueled tank, the results were disastrous. The incendiary compound ignited instantly, burning at extreme temperatures, and the damage included embedded fragments from the projectile casing. These tests made clear that whether the rounds were high explosive or incendiary, their destructive potential was extreme. Statistical records from the 8th Army Air Force between January and May 1944 provide more detail on the kinds of weapons causing bomber damage. In that period, 20 mm shells were recorded as responsible for 668 incidents, making up about 4.5% of the more than 15,000 recorded causes of damage. Rockets and 30 mm shells together accounted for only 13 cases in the same data set. It is important to remember, however, that these figures come only from bombers that were able to return to base, meaning the most catastrophic losses are not represented in the numbers. A 1947 U.S. strategic bombing survey included comparisons between German and Japanese aircraft weapons. One section of the report emphasized that American bombers had proven highly vulnerable to the Mk-108 during operations over Europe. Another document noted that while heavy-caliber weapons such as the Mk-108 were extremely effective against bombers, they were far less efficient when used against more maneuverable fighter aircraft. Photographic evidence of damage attributed directly to the Mk-108 is rare, but one image does exist of a B-17 that returned to base after being struck by a round from an Mi-262 jet. The overall conclusion is that the Mk-108 was tremendously destructive against large bombers. A few solid hits could cripple or destroy even the heaviest Allied aircraft. However, German interceptors armed with the weapon had to get dangerously close to use it effectively. exposing them to concentrated defensive fire and the constant threat of Allied escort fighters. The Mk-108 represented a deliberate trade-off. It offered devastating firepower at the cost of lower aircraft performance, a slower muzzle velocity that reduced accuracy, a lower rate of fire compared to some other weapons, and limited ammunition capacity. Despite these limitations, when rounds did connect, the results were catastrophic for Allied bombers, which is why the weapon earned such a fearsome reputation in the skies